Today we're going to move forward and talk about a concept called electric fields. Remember, for the last couple of days we've been talking about electric forces. Today we're talking about electric fields. We'll differentiate between those in just a few minutes. So let me define an electric field first. An electric field is much like a gravitational field. An electric field is a region in which an electric force could be experienced by a charged object. Like in a gravitational field was a region in which a gravitational force could be experienced by a charged object. Notice I italicized the word could. This doesn't mean that we are necessarily experiencing an electric force. It means that we could experience an electric force, or at least a charged object could experience an electric force. Now, when could an electric charge experience an electric force? Not when is it, but when could it experience an electric force? Well, probably when it's nearby another charge, right? When it's nearby something that's causing some kind of influence on it. In other words, if we have something like this, a charge that let's say is positively charged or negatively charged, whatever, and we put something nearby it, another little positive charge over here, then this positive charge could experience an electric force. Okay? Now, it doesn't mean that if we take away that thing that could experience that force, that other little charged object that could experience the force, we take it away, there's no force. It doesn't mean that the influence of this thing that's causing it all disappears. There's still a field there. Okay, the electric field is a concept that helps us to understand what's going on around this producer when there's something there to experience it, or when there's something not there to experience it, right? You got something there to experience it, there's a force. We could experience a force if we put a charge there. But even if there's no charge there, there's still something. It's like gravity, right? Right now, at this point where my board marker is, there's a gravitational force acting on this board marker, right? If I take this board marker away and hide it, there's still gravity at that point. There's just no force because there's nothing there to experience it. So how do we describe gravity at that point when there's nothing there to experience it? Well, we describe it as a gravitational field, 9.81 meters per second squared, whether there's something there to experience it or not. That's what we're doing here. We're saying an electric field is that region in which you could experience an electric force all around this producer here, but that you don't necessarily have to be experiencing a force, just that you would experience a force if you put something there to experience it. Does that make sense? Now, of course, because it's a region in which you could experience an electric force, they're going to surround electric charges. We have a positive charge right there. There's an electric field that surrounds that positive charge. If we switch that to a negative charge, the electric field would look a little bit different, but there would still be an electric field surrounding that negative charge because you could still experience a force by a charged object if we put a charged object there to experience it. So we put a little positive or a little negative there to experience it, then it would experience a force. So even though the field looks different around the negative, there's still a field there. There's still that potential influence. That's a good way to say it, a potential influence, right? An electric field potentially influences another charge if there's another charge there to be influenced. Electric fields are vector fields. There's a direction associated with them. Okay, if I have a negative producer right here, a negative thing causing this electric field, and I put a positive charge right there, it's going to experience a force towards it. But if I put a negative right there, it's going to experience a force opposite. There's clearly a direction associated with it, right? Associated with the influence. So therefore, it's got to be a vector field. Gravity fields are also vector fields, right? Every time I put this board marker at that spot in space and let it go, then the gravitational field causes the board marker to fall towards the Earth. There's a certain direction associated with the influence for both electric fields and gravity fields. So we call them both vector fields. As opposed to something like a scalar field, like a heat field or a light field, which influence things, to provide influence just like electric fields and gravitational fields do. But they don't influence things in a particular direction. It's warm right now in this room, I find. I don't know about you guys, but I find it pretty stuffy actually in this room right now. The heat is coming from these radiators in the ceiling. Why they put radiators in the ceiling, I'm not sure when heat rises, but it seems to me to be a very inefficient way of heating a room. But anyways, okay, we know that it's coming from right there and it's traveling, right? The heat is traveling from there across the room. The velocity of that heat is a vector because it's moving in a certain direction, but it doesn't influence me in a particular direction. It influences me. Yeah, I'm not going to wear a jacket. Hey, I'm not going to wear a winter coat and a toque. I'm influenced by that heat, but I'm not influenced in a particular direction. So we would say that the heat field is a scalar field as opposed to a vector field like the electric field and the gravitational field. Let's go to another page and then we'll shut her down for the day here. So we talked about this a little bit already. Fields exist as long as there is something to cause it, as long as there's a producer, right? That's the whole concept of electric fields, is to describe how there can still be an electric influence or potential influence even when there's nothing to experience it. So you've got the field there even if there is no charge out here experiencing it. Let's say this is positive. If we put something out here, a little test object out here, there'll be a force. It will experience the field, but that field is still there even if that thing that potentially experiences it isn't there. So fields exist as long as there's a producer. We don't need something to experience it. Forces, on the other hand, only exist if there's something to produce the field, like we have right here, and something to experience the field. So let's say here's the producer, and here's an experiencer out here. Clearly, if you look at these two charges, you've got a force between those two charges. If you take away the experiencer, the force is gone, because you can't have a force without two things. But it's not, this electrical phenomenon of electric fields is not gone. Just like if we have the Earth and the board marker, there's a force between them. If I take away the board marker, it's not like gravity has disappeared. It's just that the force of gravity has disappeared. We would still have the field because we still have the producer.